Hello everyone. In this video, we will be discussing the numerical on a stepped shaft. So in the last two videos, we have solved a similar type of problem, but this particular problem is having little complexity. We will just discuss what is the complexity and how to crack that one. So what is the question given is a composite shaft as shown consists of an aluminium section of 50 mm diameter and a steel section of 25 mm diameter. So this is the given sketch. We can able to see that. So this is the aluminium section and this is the steel section of diameters given as 50 mm and 25 mm. The ends of the shafts are fixed. Yes. So both left end and right end are fixed. So determine the maximum shear stress induced in aluminium and steel shaft. So they asked us to find out the maximum shear stress which is induced on this particular shaft and the torque applied which is on the first section of magnitude 200 Newton meter, and the length from the left end to the point where the torque is applied of distance 200 mm. The first aluminium bar section length is 300 mm and second steel section bar length is 300 mm. So it is little tricky. In which way means they have given the rigidity modulus for these two elements separately. So we will just see that how to find out that one. So the value given is for steel it is 84 gigapascal and for aluminium it is 28 gigapascal. Here I want to say one note. So most of the times they will give you the rigidity modulus data. Very few times in the examination they may not give the data. So that time it is mandatory from the students. They need to remember the data and they need to write it. So what are the common values they supposed to remember is it will be aluminium, steel or cast iron. Only these three data will be there. So nothing wrong in remembering these data. So first, as usual, the very important step in the entire problem is whatever the data is given that we will be writing in the required unit. And this problem we can able to see here, torque is given in meter, diameter they have given in mm, even length also they have given in mm. So it's better to keep everything in mm so that we can convert even the given torque also in terms of mm. So the d1 d2 value which is given as 50 mm, I'm not changing that, and d3 d4 also same thing. Because why I need to go means because there is a shaft is acting on, there is a torque is acting on this particular point, so obviously I need to go with this kind of requirements. So only T2 and G1 G2 for the first thing and only G3. So the values which is given in gigapascal, because in the previous video only we discussed how to convert the pascal or the meter or in terms of mm, all those things. So as per that, in case of gigapascal, if you want to convert it to Newton per mm square, it is just only the multiplication of 10 power 3. And L1, L2, L3 which is given in the question itself, I'll be following the same thing. So the very first step is finite element analysis. So I'll be going with three elements. So the first two elements consist of aluminium and the third element of steel. So we know that each node is having 1 degrees of freedom, but what all the things we need to remember here is at each node there will be a torque and even there will be a deflection, or we can call it as a slope. So for the all four nodes I'll be writing the torque and the slope as T1 theta 1, T2 theta 2, T3 theta 3 and T4 theta 4, that I'll be writing here. So node 1, element 1, element 2, element 3, node 1, node 2, node 3, node 4 is there, and the corresponding length for the elements also I have written here. So the second step is the element stiffness matrix. So we know the formula, it is Gj by L, 1 minus 1 minus 1 1. So for the element 1 it is G1 J1 by L1. And what is the J value? We know the diameter for the first section, that is for the first element, which is nothing but 50 mm. So and we know the formula for the circular cross section, the polar moment of inertia is pi by 32. So pi by 32, D is 50. So D power 4. So after simplification, we will be getting 6.75 into 10 power 5. And I will be substituting, I know the G value, J value also I know that in terms of mm, and L value again it is in mm. After substituting and simplification, I will be getting 10 power 7 of 8.582, and the this is a positive location, this is a positive location, and this is a negative location, this is a negative location. Since for the element 1, the node numbers are 1, 2 and 1, 2. Now moving to the element 2, the formula will be G2 J2 by L2, 1 minus 1 minus 1 1. So I will be substituting, since the J2 remains same, I will be substituting the J2 value. G2 is again for aluminum it is same, and L2 value is different, that is 100. I will be substituting everything in the formula. After simplification, I will be getting the value is 17.164 in this location, and minus 17.164 in this location, and minus 17.164 in 2 3 location, and plus 17.164 in 3 3 location. For the element 3, the element stiffness matrix formula is G3 J3 by L3, 1 minus 1 minus 1 1, and J3, since the diameter is 25, after substituting in the pi by 32 d power 4 formula, that is pi by 32 25 power 4, from the simplification I will be getting 3.834 into 10 power 4. I will be substituting that value here, and the G value, rigidity modulus in terms of Newton per mm square, I will be substituting this, and L3 is 300. I will be substituting here. After substituting 10 power 7 common value, I will be getting outside, and the location of 3 3 is 1.0735, and for 4 is minus 1.0735, and 3 4 is minus 1.0735, and 4 4 is 1.0735. So the global stiffness matrix, which is nothing but assemblage of all the element stiffness matrix, that is capital K equal to K1 plus K2 plus K3. Since 4 nodes are there and each node is having 1 degrees of freedom, so degrees of freedom into number of nodes, that is 4 into 1, which is equal to 4. So the order of the matrix should be 4 cross 4. So I will be writing first the order 4 cross 4, and I will be adding up each locations. Example 1 1, 1 2, 1 3 and 1 4. After adding all those values, again we need to cross verify whether it is having the properties of the stiffness matrix. We can able to see here the main principal leading diagonal is having a positive value, and there is no zero value, and there is no negative value, so it is right. And first row first column, second row second column, third row third column, fourth row fourth column, it is same. So it is a symmetric matrix, and even it is a banded matrix. So we can say that it is fulfilling all the properties of stiffness matrix, so it is right. Next step is the angle of twist and the tension. Since 4 nodes are there, so theta vector, that is the slope vector, will be equal to, for the all 4 nodes, theta 1, theta 2, theta 3, theta 4. Similar for the torque, it is T1, T2, T3, T4. Since only at node 2 only the torque value is given, that I will be substituting in terms of mm, that is Newton per mm. So remaining all the nodes, since the torque value is not given, so it is 0. So the equilibrium condition, that is K into theta vector, which is equal to T vector, I will be substituting whatever the matrices which I have found in the previous steps. And what is the boundary condition? The boundary condition is very clearly defined, that is node 1 and node 4 is fixed. So I will be following the elimination approach method. So I will be eliminating the first row, first column, and even the fourth row, fourth column. After eliminating these values, that is only these matrices left out, is so clear that only theta 2 and theta 3 we need to find out. Either by the manual method or by the calculator, we will be finding out this one. And this is theta 2 and this is theta 3. Both the values I will be getting in the unit radians, and both the values I am getting in positive. It means that since the torsion value they have substituted positive, even the rotation also will be getting in positive direction. The next step is the determining the element shear force. The formula, rigidity modulus into radius divided by length. For the element 1, it is tau 1 equal to G1 R1 by L1. R1 is nothing but the radius of the first element part, which is nothing but 50 by 2, which is 25. After substituting in this particular thing, since theta 1 is 0, theta 2 value we know that, tau 1 will be getting it as we will be getting as 7 into 10 power 8 Newton per mm square. Similarly for tau 2, it is G2 R2 by L2. Since R remains same, 50 by 2 25, I will be getting same thing. Theta 3 is 0. After the simplification, I will be getting this. Then moving to the tau 3, it is G3 L3 by G3 R3 by L3. R3 already radius for the third element is 25, so radius will be 25 by 2. Diameter is 25, so radius will be 25 by 2. So substituting in this, and we will be getting this thing. And here, what is the interesting thing you can able to see here is, for the element and element 2, the shear force will be getting in terms of positive, and for the element 3 will be getting it is negative. It means that the torque which is applied on the node 2 was responsible for the negative side of the shear force on the element 2. So if you have any doubt with this particular problem, please post your doubts in the comment section. Thank you.